Good morning, dear students. Our next session deals with the point groups. Okay, so point groups here means here the elements of symmetry of a crystal. We have seen some of the elements of symmetry. That is, what are the elements of symmetry for a crystal? That is, we have got planes of symmetry. Then the second one, that is the axis of symmetry or axis of symmetry for plural. Then the third one, that is the center of symmetry, isn't it? So based on these elements of symmetry, see there are 32 different combinations are there. Okay, 32 different combinations for the symmetry elements are there for a crystal system. Okay, so this is a theoretical basis. That means there are 32 different combinations of the elements of symmetry for a crystal. So that means 32 different combination means it will be corresponding to 32 point groups. Okay, 32 different combinations of the symmetry elements means it will be corresponding to 32 point groups. So based on these these different combinations or these 32 point groups, we can group together these 32 point groups into 7 basic crystal systems. Okay, so these 32 point groups, based on some different characteristic features, they are grouped into 7 basic crystal systems. Okay, so this 32 point groups, it is grouped to 7 basic crystal systems, so that the studies about these crystal systems, it will be easy. That means we are grouping some characteristics, and based on that characteristics, these point groups are grouped into 7 basic crystal systems. And again, these 7 basic crystal systems are the first one, that is the cubic system or the regular system that we have seen. Just like the crystal system, it will be having the shape of a cube. Okay, so that is the first system. Then the second one, that is the tetragonal crystal system. Then third one, it is the orthorhombic system. Then fourth one, it is the monoclinic. Then fifth one, hexagonal. Then sixth one, rhombohedral. And the seventh one is triclinic. So these are the 7 basic crystal systems: cubic, then tetragonal, then orthorhombic, then monoclinic, hexagonal, rhombohedral, and triclinic. So these are the 7 basic crystal systems. And again, you have to, in your textbook, there is a table given, and you have to study the different symmetries or the different symmetry elements for all these systems. Okay, so for this cubic or regular system, it has got 9 planes of symmetry we have seen, isn't it? 9 planes of symmetry for a cubic system plus 13 axes of symmetry. Okay, so the apart from that, there will be one center of symmetry also. So here we will be dealing with the planes of symmetry as well as the axis of symmetry. Okay, so first of all, I will be writing the planes of symmetry, then comes the axis of symmetry. So for a cubic system, it has got 9 plus 13. Okay, then for a tetragonal system, it has got 5 planes of symmetry and 5 axes of symmetry. Okay, 5 planes and 5 axes of symmetry. Then for an orthorhombic system, it has got 3 planes of symmetry and 3 axes of symmetry. Then for a monoclinic system, it will be having 1 plane of symmetry and 1 axis of symmetry. Then for hexagonal, it has got 7 planes of symmetry and 7 axes of symmetry. Then for rhombohedral, again it has got 7 planes of symmetry plus 7 axes of symmetry. Then for triclinic, there will be no plane of symmetry as well as no axis of symmetry. Okay, so this is regarding the symmetry elements of all these 7 crystal systems. Okay, so only in the case of cubic system, it has got 9 planes of symmetry and 13 axes of symmetry. And also you have to go through some of the examples given in your textbook. See, sometimes these examples might be asked. So this cubic system, example for a cubic system, the most familiar example, that is sodium chloride crystal, then potassium chloride, calcium fluoride, etc. So many examples are given. Then diamond, it is also an example for a cubic system. Okay, so likewise so many examples are given in your textbook for all these 7 basic crystal systems. Okay, so you have to study that examples, you have to go through that example. Sometimes it may be asked in your section A part. So this is regarding the point group. So point groups means 32 point groups means it will be dealing with the 32 different combinations, and they were again grouped together to 7 basic crystal systems, and the 7 basic crystals are these 7: cubic, tetragonal, orthorhombic, monoclinic, hexagonal, then rhombohedral as well as triclinic. Okay, then the next one, that is the crystal lattice and unit cell. Crystal lattice and unit cell. Crystal lattice and unit cell. See here, crystal lattice and unit cell means, you see here for sodium, for example, in the case of a sodium chloride crystal, it is having Na plus ions as well as Cl minus ions, isn't it? So here, while we are dealing with this crystal lattice or unit cell, we are considering all these atoms or all these ions as just points. Okay, so instead of Na plus, you will be marking it as a point or a dot. For Cl minus also there will be a dot. So here in while representing this crystal lattice or unit cell, we will be marking it as some points. Okay, so here so we can say that these constituent particles or ions or molecules, so these points may be this atoms. Points can be atoms, or it can be molecules, or it can be ions. Okay, so this is the case. And also see, suppose this points, when it is arranged along a straight line. Okay, so suppose these points are arranged along a straight line, and also these points must be equal distance. Okay, if these points are at equal distances and also arranged along a straight line, we can call it as a one-dimensional lattice. Okay, so this type of lattice points we can call it as a one-dimensional lattice. Only thing is that these points, it will be represented in a straight line, and also it will be equidistant from each other. These points will be denoting these atoms, whether it can be atoms or it can be molecules or it can be ions. So this is the case of a one-dimensional lattice. Then coming to the two-dimensional lattice, normally, as you know, this two-dimensional lattices means it will be having 2 axes, isn't it? One x-axis as well as the y-axis, isn't it? So here also for a two-dimensional lattice, we can say that 2 vectors will be there. Okay, or 2 dimensions or 2 axes will be there. So here the 2 vectors are denoted by A and B. Okay, so for a two-dimensional lattice, it will be having 2 axes or 2 vectors A and B, and these 2 vectors will be along the 2 axes x as well as the y axis. Okay, so these 2 vectors will be along the x and y axis. And also one more point here to be noted is that, see, between these 2 axes, that is, suppose this is the x axis and this is the y axis. Okay, so let this distance, let it be A, and this distance, let it be B. Okay, so you know that, see, one angle will be there in between these 2 axes, isn't it? So we can say that for representing a two-dimensional lattice, we can say that 2 vectors are there along with an angle. Okay, an angle will be there between the 2 vectors. An angle will be there between the 2 vectors. So that is called as a two-dimensional lattice. So this is a two-dimensional lattice. Two-dimensional lattice. Okay, so here then this is the case of a two-dimensional lattice. Then the next one, we have to go through the three-dimensional lattice. See here, for a three-dimensional lattice, we can say that there will be how many vectors? 3 vectors will be there for a three-dimensional lattice. For a three-dimensional lattice, 3 vectors will be there. That is, the 3 vectors will be, the basic vectors will be A, B as well as C, and will be at 3 axes, along 3 axes, that is X, Y as well as Z axis. Okay, so here this, if see, suppose for a two-dimensional lattice, I forgot to write the dot. Okay, so this is the case of a two-dimensional lattice. Okay, two-dimensional lattice. Example for a two-dimensional lattice. Two axes will be there, x as well as the y axis. Okay, so here in this three-dimensional lattice, there will be, we can represent using three vectors a, b, c along three axes, x, y and z axis. Okay, so here if similar points were connected by a set of parallel lines, if similar points were connected by a set of parallel lines along x, y and z axis. Okay, along x, y and z axis, then we can call it as a three-dimensional lattice or a space lattice. Normally this three-dimensional lattice, it is called as a space lattice or a crystal lattice. Space lattice, or we can say it as a crystal lattice. So here three-dimensional lattices means there will be three vectors and also three angles will be there in the case of a three-dimensional lattice. Okay. So this a crystal lattice or space lattice, we can define it as an array of points. Space lattice or crystal lattice means it is an array of points showing the arrangement of atoms, or ions or molecules, arranged at different size in three-dimensional space. Arranged in three-dimensional space. So it is called as a crystal lattice or a space lattice. So simply we can say that a three-dimensional lattice is a space lattice or a crystal lattice. So it is an array of points showing how these atoms or ions or molecules are arranged in three-dimensional space. And also see, this three-dimensional lattice, it is built up of unit cells. Okay, three-dimensional lattices, they are made up of using unit cells. So we can say that this unit cell means it is the smallest repeating unit. Unit cell, it will be the smallest repeating unit in the space lattice. It is the smallest repeating unit in the space lattice. Say for example, I will take the cube. Just wait. Sorry. See, this is a Rubik's cube and see, this is a crystal lattice. We can say it as a crystal lattice. That means it has got three vectors. That is, see, consider this corner. Okay, so this is one axis. This is x axis. This is the y axis and this is the z axis. Okay, x, then y, then z. Okay, so we can say that this length, we can consider any length as a. Okay, and this length b and this length c. Okay, so here while considering this case, so this as a whole, this is a crystal lattice, and see this each square part. Okay, if I am taking this one square piece outside, then we can call it as a unit cell. That means this one piece. Okay, this one piece we can call it as a unit cell. That means that it will be repeating these unit cell, it will be repeating to form a crystal lattice. See, so many unit cells are there, so that a cube is formed or a crystal is formed. Okay, consider this as a crystal, and each piece or each part, this part, we can call it as a unit cell, and this unit cell, it will be repeating, and so it will be forming together as a crystal lattice. Okay, so for a crystal lattice, it will be having three axes. This is the x-axis, y-axis and the z-axis. Okay, you can consider any three axes, that is the x, y and z, and correspondingly the length of each axis, we can consider it as a, b as well as c. Okay, so hope you are clear with the space lattice as well as the unit cell. So we can define this unit cell as the smallest repeating unit in the space lattice. Okay, and which when repeated again, it will be resulting in the formation of a crystal. So each unit cell, see here, each unit cell will be repeating. See, this is one unit cell, this is another unit cell, then another one, another one, another one. This is another one. Like that, it goes on. So this repeating units, which when joined together or which when repeated over and over again, it will be resulting in the formation of a crystal. Okay. So that is the definition for a unit cell. Then the next one, see, I am representing here this cube. See, this is a cube, and also here you have to represent the points, that is A, B and C, the three vectors. This is vector A and this is vector B and this is vector C. Okay. So here also I am taking this particular axis, that is these three axes. Okay. And I am taking it outside these three axes. I am drawing here. Okay. The first one, then the second one, and then the third one. Okay. The three axes. Let it be X, Y and Z. Okay. So this is X, this is Y and this is Z axis. You can take it anyway. Okay. So here this axis to the X axis corresponds to the vector A. So distance A. Let it be up to this distance. Let it be A. Okay. Then this distance it is B. So let it be B here. And again this distance let it be C. Okay. So the three distances A, B and C. Then again, three angles will be there. See, here one angle will be there, another angle and the third angle will be there. Okay. So this, the angle opposite to the distance A, let it be alpha. Okay. So this distance, this angle, let it be alpha. That is just opposite to A. Okay. Let it be alpha. Then here, the angle opposite to B, let it be beta. Okay. Here it is beta. And then the angle opposite to C, let it be gamma. Gamma. Okay. So this is, that is, I am taking these three axes separately and drawing it here. And this is the X axis, this is the Y axis and then the Z axis. The unit distances are denoted by A, B and C. And the angle opposite to A, let it be alpha. The angle opposite to B, let it be beta. And the angle opposite to C, let it be gamma. So this is the simple representation for a three-dimensional unit cell. Okay. So this is a three-dimensional unit cell, isn't it? This is a 3D unit cell. And also see here the distances A is equal to B is equal to C, isn't it? Almost all are the same distances. So A is equal to B equal to C. And also the angles alpha is equal to beta is equal to gamma. Okay. So this is the definition or this is the representation for a unit cell and you have to mark the angles as well. Okay. Then the next one, you have to calculate the density of the crystal. Okay. The density of a crystal, it can be calculated by the formula density. Density usually it is denoted by the letter rho. Density is equal to small n into capital M divided by Na into V. Okay. Small n into capital M divided by Na into V. Okay. So here small n means it is the number of particles or the number of atoms or the number of ions. Okay. Whatever species, let it be small letter n. Then capital M, as you know, it is the molar mass. Capital M is the molar mass. Then what about Na? Na is the Avogadro number. Na is the Avogadro number and capital letter V, let it be the volume of unit cell. Capital V, let it be the volume of the unit cell. So this is the formula for calculating the density of a crystal. So density rho is equal to N into capital M divided by Na into V. This formula, it is very, very important. You have to study and also some problems are there with this problem. Okay. In this formula. Okay. So density rho is equal to N into M divided by Na into V. Then the next one, another important topic, that is the Brevis lattices. Hope you are clear up to this much. Then the next one, that is the Brevis lattices. B-R-A-V-A-I-S. Okay, Brevis lattices. So here this Brevis lattices, the French crystallographer, he is Brevis, in the year 1848. He said that there are 14 different ways for arranging similar points. Okay, that means there are 14 different ways for arranging similar points in three-dimensional manner or in three-dimensional order. That means there are 14 different ways of arranging the 7 basic crystals. That is, in total, we all know there are 7 basic crystal systems, and these 7 basic crystal systems, they can be arranged in 14 different ways. Okay, or we can say that, in other words, the total number of space lattices belonging to all the 7 basic crystal systems, that will be equal to 14. The total number of space lattices, belonging to all these 7 basic crystal systems, it will be equal to 14. That is, this is called as Brevis lattices, or there are 14 different ways in which we can arrange this space lattices in a three-dimensional manner. Okay, or there are the total number of space lattices belonging to all the basic crystal systems will be equal to 14. And also there are 3 kinds of, in the case of various unit cells, there are 3 types of lattice points. Okay, 3 types of lattice points are there. 3 types of lattice points, and the first one, that is the simple or primitive lattice. Then the second one, that is the face-centered crystal lattice. Face-centered crystal lattice, or we can say it as FCC, face-centered crystal lattice. The third one, it is the body-centered lattice. Body-centered, that is BCC. Okay, simple or primitive, face-centered, then body-centered cubic lattice. FCC means face-centered cubic lattice. BCC means body-centered cubic lattice. Then you have to see how many atoms are there in a simple or a primitive lattice, for a face-centered cubic lattice and for a body-centered cubic lattice. Okay, so first of all, you have to see the case of a simple or a primitive lattice. Simple or a primitive lattice. Okay, see here, for a simple or primitive lattice, if the points are at the corners, we can say that it is a simple or a primitive lattice. See, in the case of these are saying in the case of a cubic lattice. Okay, these 3 types of lattice are in the case of a cubic crystal system. Okay, so for a cubic simple or a simple cubic system or a primitive cubic system, we can say that the points are all at the corners. See how many corners are there for a cubic system? 1, 2, 3, 4. Then below this part, 5, 6, 7, 8. Okay, 8 corners are there. So total 8 corners are there for a simple cubic lattice. See, we can say that each corner, see, at each corner there will be an atom, isn't it? And also at each corner, this atom will be shared by another 8 atoms. How? That means at this point, this atom, it will be shared by 8 other atoms. That means, see here, suppose, and you can consider this point. Okay, at this corner, see, this atom, it is shared by 4 atoms here, isn't it? That is, this atom, it will be shared by 4 other unit cells, isn't it? Likewise, 4 unit cells will be above this point also, isn't it? That is, we are taking the case of a unit cell at this particular point, or an atom at this point, and this atom, it will be shared by these 4 unit cells. Okay, also above these 4, there will be another 4 atoms are there, or another 4 unit cells are there, isn't it? So this the atom at this particular point, it will be shared by how many unit cells? 8 unit cells, isn't it? 4, this 4, then also 4 above these 4. Okay, so in total, one atom, this atom, it is shared by 8 unit cells. So we can say that in total there are 8 corners, isn't it? 8 corners are there So 8 corners means for each corner it will be shared by 8 other atoms. So in effect we can say that how many atoms will be there total for a simple cubic system. There will be one atom. Okay, there will be only one atom. Then one atom or one point, we can say that it is a point. So if there are points only at the corners, we can say that it is a simple or a primitive lattice, and also the number of atoms in a simple or the number of atoms in effect will be equal to 1 in the case of a simple or a primitive lattice. Okay. Then the next one, that is the body-centered cubic lattice. Body-centered cubic lattice. So here the contribution, the total number of atoms per unit cell. So if this is a simple or a primitive lattice, we can say that the total number of atoms per unit cell, it will be equal to 1. That is, for this particular unit cell, the number of atoms in effect will be equal to 1. The number of atoms per unit cell, it will be equal to 1 for a simple or a primitive lattice. Then the next one, the second one, that is the face-centered cubic lattice, or FCC, face-centered cubic lattice. So here in the case of the face-centered cubic lattice, the number of atoms we have to consider by considering the number of corners. There will be contribution from the corners as well as from the faces. Okay. There will be contribution from the corners and also the contribution from faces. So here, if we are considering a face, so here I am considering this particular face, or this we have to consider this particular unit cell. Okay, so here this is a face for this unit cell, isn't it? So here one atom, if one atom is here, what happens? This atom will be shared equally by this particular unit cell as well as the one above this unit cell. Okay, are you clear? That means, see here, if an atom, this is a unit cell, and if an atom is present here, this is one face of this unit cell, and if an atom is present here, what happens is that this atom will be equally shared by this particular unit cell and also one above this unit cell. Okay, that means another unit cell which is above this plane. Okay, so one atom, it will be shared equally by 2 unit cells. That means in effect, how many faces are there? So for one face, it will be having half of an atom, isn't it? So for one face, it will be having half of the atom. And also for a cubic system, how many faces are there? 6 faces are there. We have seen in our last class, isn't it? So in effect, so total 6 faces are there. So each face will be sharing half. So half into 6 plus the number of atoms from the corners, or the contribution of the 8 corner atoms that we had already seen. That is, contribution of 8 corner atoms means 8 into 1 by 8. So in effect, for a face-centered cubic lattice, how many are there? See here, 1 plus 3. That is in effect 4 atoms. So in a face-centered cubic lattice, we can see that the number of atoms per unit cell, it will be equal to 4. The number of atoms per unit cell, it will be equal to 4 for a face-centered cubic system. Okay. So here the face-centered means it is the addition of the number of atoms contributing from the corners as well as the number of atoms contributing from the faces. Then the third one, that is the BCC, or the body-centered cubic lattice. Body-centered cubic lattice. See here, the contribution for the body-centered cubic system, it is from the corners and also from the center of the crystal. Okay, the body-centered, the contribution, it is from the corners as well as from the center. Okay, so here from the corners means, we had already seen corners means the contribution will be 1, that is 8 into 1 by 8 plus center. See, in center of the unit cell means, see, within the unit cell, that is at the center of this particular unit cell, that is inside this unit cell. Okay, within this unit cell, there will be one atom which is not shared by any of the faces or corners or edges. Okay, that is within this unit cell or inside this unit cell, at the center of this particular unit cell, one atom will be there, and that particular atom, it will not be shared. That particular atom, or it can be a molecule or an ion. We are considering it as a point. Okay. So that particular atom, it will not be shared by any of the edges or corners or faces. Okay, so that contribution means it will be 1. So the contribution from the center, it will be 1, a single atom. So in total we can say that in the case of BCC there will be 2 atoms. The number of total number of atoms per unit cell in body centered cubic lattice, it will be equal to 2. Okay, so this is very important, the number of the contribution per unit cell. Okay, so the number of atoms per unit cell in a simple or a primitive lattice, it will be equal to 1. For an FCC, it will be equal to 4. For BCC, it will be equal to 2. Okay, hope you are clear up to this. So in our next session, we can go through some of the problems also regarding these crystal systems. Okay, and also the next topic, that is the crystal systems, and you have to go through some of the lattice types and the angles in between, and also the density should be calculated in our next session. Thank you.